Hello and welcome to Tech Learners. Let's understand one more definition in the relation chapter. And today we will understand what we mean by partial order relation. In the previous lecture, we had seen what is equivalence relation. And today we will see what is we mean by partial order relation. So let us define first partial order relation. In the same manner, let a relation R defined on a set A defined on a set A such that it follows all these three conditions. First condition is R is reflexive, which means for all elements, for all X belongs to set A, X should relate to X, which means X comma X should belongs to R. The second condition is R should be anti-symmetric. R should be anti-symmetric, which means for all, not for all actually, for two elements X and Y, for two elements X and Y that belongs to set A, if X is related to Y and Y is also related to X, then this is only possible whenever X is equal to Y. Else, this should not be possible. So, this is the condition for anti-symmetricity. The third condition is transitivity, which means R should be transitive. That means for three elements X, Y, and Z that belongs to set A, if X is related to Y and Y is also related to Z, then X should also relate to Z. So this is transitive. So now for any relation to be a partial order relation, all these three conditions must be true. R must be reflexive, R must be antisymmetric, and R must be transitive. If any of the three conditions do not satisfy, then R will not be the partial order relation. Now let's see an example. Let us say that there is a set A which elements 1, 2, and 3, and a relation R is defined on A, which is from A to A, in such a manner that it contains ordered pairs x comma y such that x divides y, such that x divides y whenever x and y are the elements of set A. So before we check whether this A is a partial order relation or not, let's form whether this R is a partial order relation or not. Let's form the relation R. So what will be the ordered pairs of R? Let's see. We'll start from this A as it is defined from A to A. So we'll take first element 1. So let's see. 1 comma 1. Yes, this will be there at 1 divides 1. Then 1 comma 2 will be there as 1 divides 2. 1 comma 3 will be there as 1 divides 3. Next is we'll start with 2. 2 comma 1 will not be there because 2 does not divides 1. So the next ordered pair would be 2 comma 2. 2 comma 3 will also not be there because 2 does not divides 3. Then we have 3. 3 comma 1 will also not be there as 3 does not divides 1. 3 comma 2 will also not be there as 3 does not divides 2. And lastly, we will have 3 comma 3 as 3 divides 3. So this is the relation that we are talking about. And we have to check whether this relation is a partial order relation or not. So let's check for the first condition, reflexivity. Now we can see for all x that are belonging to set A, x divides x. any element divides itself, we all know. So which means that all x are related to themselves. We can see for 1, 1 comma 1 is there, for 2, 2 comma 2 is there, and for 3, 3 comma 3 is there. So we say that R is reflexive. R is reflexive. Now let's check the second condition, that is for symmetricity. Let's say we take any two elements x comma y that are belonging to A, such that x is related to y and y is also related to x. This is only possible whenever x is equal to y, right? So let's see for this first order pair, let's say it's 1 comma 1. So for 1 comma 1, and we also have 1 comma 1, both are true, and this is resulting in 1 comma 1, which is in the relation R. The next is 1 comma 2, and we see that for 1 comma 2 we do not have 2 comma 1 in this. Next is 1 comma 3. For 1 comma 3 we also do not have 3 comma 1. Then for 2 comma 2, yes, for 2 comma 2 we have 2 comma 2, which results in 2 comma 2, which is true. So this condition is true and this condition is true, and the last one is 3 comma 3. So we have let's say this 3 comma 3. So for 3 comma 3 we also have 3 comma 3, and this is resulting in 3 comma 3. So for this also it is true. So we can see the condition is only true. Which condition? If x is related to y and y is also related to x. So this condition is only true in this case whenever x and y both are equal to each other. So this is resulting x is equal to y. You can see here also, we can see here also, and we can see here also. So this is only true whenever x and y both are equal to each other. Otherwise, this is not true. So we say that this is anti-symmetric. So this is hence R is anti-symmetric. It's basically anti-symmetric. Now let's check for the third condition whether R is transitive or not. So let me write this R once again here. So we have 1 comma 1, we have 1 comma 2, we have 1 comma 3, we have 2 comma 2, and we have 3 comma 3, right? So for transitivity, we know we follow all the conditions. It's like if x are y and y are z, then what should be true? X should relate to z. So let's find all these primary conditions. We'll start with 1 comma 1. Now for 1 comma 1, we have this 1 comma 2, and this should result in 1 comma 2, which is there in the relation. Next is for 1 comma 1, we have this 1 comma 3, for which also we have 1 comma 3. This is also true. So this is true for all 1 comma 1 ordered pair. Now let's pick the next one for 1 comma 2. For 1 comma 2, there will be only one condition with this ordered pair 2 comma 2. The resultant should be 1 comma 2, which is already there in the relation. So this ordered pair is also done. Let's take the next ordered pair, which is 1 comma 3. For 1 comma 3, only one primary condition will hold, that is 3 comma 3, whose resultant is 1 comma 3, which is also there in the relation. Next is 2 comma 2. So for 2 comma 2, we have only 2 comma 2. So again, the 2 comma 2 is present there. So this 2 comma 2 can be related with 2 comma 2. The resultant is 2 comma 2 only, which is true. And similarly, the last one, 3 comma 3, we have only one condition for 3 comma 3, that 3 comma 3 is equal to, so this will result in 3 comma 3, which is also there. So we see all the conditions are true for transitivity, and hence we'll say that R is transitive. And as we already know from the relation given, that if x divides any element, let's say y, and y divides any other element z, then we all know that definitely x will divide z. So we say that R is transitive. So from all these three conditions, we see that X is in this condition. So this R is reflexive, R is antisymmetric, and R is transitive. So this relation is the partial order relation. So the given relation defined in this way is the partial order relation.